Hi, Year 13. Let's have a look at your HL content for C1, C2, C3 in your assessment. So this went really well for you for the year group that I'm recording this for, but just in case there are a couple of bits that you need to pick up on. So question 1 was a single slit question. You have light of intensity I and wavelength lambda incident on a single slit, so immediately you should be writing to yourself the single slit equation of slit width W, but obviously that is B in the equation, so label that. You've got an interference pattern formed. What change will increase the width of the central maximum? So if you increase the width of the central maximum, you're essentially increasing theta, because obviously that's measured from this central point. So to increase theta with the same wavelength, you have to decrease B. So you have to therefore decrease W in this question. So that's just recognition of what is what in the equation, and knowing that an increase in width of the maxima means increasing theta. So in question 2, white light is incident on a diffraction grating. The second order maximum of wavelength 600 nanometers falls directly onto the third order maximum of a wavelength lambda. What is lambda? So obviously you've got two different patterns to consider, but if they overlap, if they fall directly over each other, then theta is the same for both scenarios for them to reach the same point on the screen. So n lambda is d sine theta. That would be constant because obviously the diffraction grating hasn't changed, it's just the order of the maxima that you're interested in. For theta to be the same, which is what we've said has to be true if they're falling directly over each other, and the slit separation hasn't changed. The only two things that are changing are n and lambda, so the order and the wavelength that would produce that order at that particular angle. So n lambda must therefore be constant. So if a 600 nanometer wavelength is used, the second order maxima would be found at d sine theta. That would be found at exactly the same place if you used a light source with a different wavelength, but for the third order maxima. So 3 lambda would equal 2 times 600, and then it's just rearranging. In question 3, this was a tricky one. I think this is one of the longer questions on the paper. So you've got an object performs simple harmonic motion. When the displacement of the object is x0 over 2, so displacement at any point is x. So in your data booklet, these equations for energy in simple harmonic motion refer to x. X in this context is equal to x0 over 2. When the displacement is that value, the kinetic energy of the object is equal to E. What would the total energy of the motion be? Okay, so we start by saying, well, the total energy is the sum of the potential and the kinetic. I've been given the expression for kinetic. I've been told that it's equal to capital E. I take my potential energy equation from my data booklet, a half m omega squared x squared, but x in this context is x naught over 2. So if I square that, I get x naught squared over 4. So I'm going to replace this x here, this x squared here, with x naught squared over 4. So that my total energy is now the kinetic energy I had before plus this expression for potential energy in terms of x naught. But what you should also notice is that the total energy at any point for an object in simple harmonic motion is a half m omega squared x naught squared. I can mathematically express my potential energy in terms of a half m omega squared x naught squared. It's a quarter of that. But now I can say that this part is equal to the total energy, because that's what total energy is equal to. So therefore, I now have this new expression that total energy is a quarter of the total energy plus my kinetic energy at that point. And then I know that to get E by itself, I can say that that is equal to 3/4 E total, because I've got a whole E total minus a quarter E total would equal to E. And then it's just a case of rearranging, because I'm asked what E total is in terms of E, and that gets me 4 over 3. That's a lot of mathematical manipulation for 1 mark there. That is a tricky one on the paper. Might be worth just kind of pausing, because listening to me speak it out might not be very helpful. But remember, it's just about energy conservation, taking your total, substituting what you know in, and rearranging. Make sure you can follow each step for me. So in question 4, an interference intensity pattern is obtained in an experiment with 4 slits. What change occurs when the number of slits is increased, but the separation of the slits and the width of the slits do not change? So all we've done is we have introduced more slits that light can travel through. We should remember from I gave you a sheet of paper with what happens as the number of slits in a diffraction grating increases, and I said to you, you really do have to remember how the pattern changes. It's for questions like this. With 4 slits, you basically now have more opportunities for destructive interference to occur. It narrows the maxima, so you get thinner beams, so the width of the primary maxima will decrease. So that's just an important one that I said that you need to remember. Question 5. So monochromatic light is incident on a single slit to form a diffraction pattern on a screen. The width of the single slit is then halved. So immediately I'm writing myself my equation for single slit diffraction. If the width of the slit is halved, then B is times a half, which means that theta will be times 2, so the width of the central maximum will increase, so I'm immediately getting rid of A and B. Obviously, if the width of the slit is halved, I now have total light going through that slit is going to decrease because it's just a smaller slit now, so the intensity will drop, which gets me C. In question 6, the pattern observed when white light passes through a diffraction grating. So we looked at these in the classroom when we looked out at white light, and we know we should see a rainbow, so that should already narrow it down a little bit. But again, we've got n lambda is d sine theta, so we know that the angle to a maxima is proportional to the wavelength. We know that the red wavelength of visible light is larger than the other colours, so therefore theta for red will also be larger. So if you're measuring out from that centre, that angle will be largest for red. That gets you C. That's one to kind of remember. 7, the intensity pattern of monochromatic light is lambda projected onto a screen. What combination produces this pattern? Okay, so hopefully you can see we have a single slit envelope where we've got maxima and minima, but that's happening over the double slit interference pattern. So remember that for the SL students, we said that the double slit introduces this series of maxima, minima, where you've got constructive and destructive interference. But single slit diffraction modulates that, so you can see that over the top. So we must have we've got double slits producing that pattern. That's just something you should remember. But also, the next bit is kind of common sense, really. It should be that you understand that the light that we're using here has a very, very small wavelength of the order of nanometers. It's not practically possible to have the width of the slits being smaller than that, so we are going to choose greater. We've got to sometimes just apply a bit of common sense to get us our answer quickly. In question 8, a simple pendulum. Again, immediately write the time period for the simple pendulum. Has a time period T on Earth. It's taken to the moon. The gravitational field strength is now a sixth of that on Earth. So G is times a sixth. 2 pi and L have been kept constant, so T is proportional to root 1 over G. If G is changed by a factor of 6, I'm just saying that T is therefore changed by a factor of root 1 over change in G, and that is equal to 1 over a sixth, which is equal to 6. So it's just times by root 6. That's just mathematical manipulation there. In question 9, light of intensity lambda is diffracted after passing through a very narrow single slit, write your equation, of slit width x. Again, B is x in this case. The intensity of the central maximum of the diffracted light is I0. The slit width is doubled. What is the intensity of the central maximum and the angular position of the first minimum? So, if the slit width is doubled, you've got 2 times the amount of light let through. So you've got 2 times the original intensity. We haven't got constructive interference here, remember, so we don't double the amplitude of the light. The light was the light, it's just we've got more of it. So it's not a case of intensity is proportional to amplitude squared, because we don't have two light sources meeting and their individual amplitudes superposed. That's not what we've got. We just have a source that is now a more intense light source. So we've got double the light source, so that's 2I0. And then obviously B has doubled, so theta is going to have halved. So that gets me, sorry, ignore me, not theta. Start again. So if the slit width doubles, B doubles, which means that this whole thing halves. Theta, the angle to the first maximum, is now going to have halved, and so that gets me to B there. Last multiple choice, question 10. So you've got a diagram where you've got an interference pattern. You literally need to count the number of fringes between that 1 centimetre. If you count across, there are 10 fringe separations in 1 centimetre. So one fringe separation is 1 millimetre. Turn that into metres. You are told the wavelength. You are told the distance, capital D, because you're told that the screen is 1 metre from the slits. We take our equation for double slit. Remember, that's not in your data booklet. S is lambda big D over little d. And then it's just substitution and rearranging for D. Things you have to have basically been able to do for this question. It's quite a lot for mark. Count the number of fringes, convert that into one fringe separation in metres, recall your equation that you can use, and rearrange. Okay, question 11. So the theory stuff, this is where we lost slightly more marks. So you've got a vertical solid cylinder of a uniform cross-sectional area, A, floating in water. The cylinder is partially submerged. So when it floats at rest, a mark is aligned. So you've got the rest position. It's then being displaced down so that the mark is X below the water surface. And then obviously as it's released, it's going to bob up and down repeatedly around the water surface position. So at time t is 0, the cylinder is released. The resultant vertical force, which is obviously in the same line as the restoring force in simple harmonic motion, because the equilibrium is this horizontal line, we are told F is minus rho AgX, where rho is the density of the water, A, you're told, is the cross-sectional area, so that's fixed. Rho is fixed, G is obviously a constant. And then it asks you to outline why the cylinder performs simple harmonic motion when it's released. So we know that the defining proportionality statement for simple harmonic motion is if acceleration is proportional to negative displacement. Acceleration is proportional to resultant force, which we're given here. So if we have simple harmonic motion, then the force should be proportional to minus x, which we can clearly see is true because rho A and G in the equation are all constant. So F is proportional to minus x, and that's all we needed to write. In B, the mass of the cylinder is given. You've got the cross-sectional area, you've got the density. Show that the angular frequency of oscillation is about 4.4 radians per second. So we are looking for omega. Again, remember our defining equation. A is minus omega squared x. A is resultant acceleration, comes from resultant force divided by mass. The force is up here. I'm going to take that expression for force, divide by mass, so that that is equal to acceleration, and that is equal to minus omega squared x. I can cancel x from both sides of the equation. The negative is on both sides of the equation. So omega squared is equal to rho Ag over m. Square root all of that, and you get to 4.43 radians per second, which is what you're trying to prove. Remember, when you've got to show that question, your answer always needs to have more decimal places than the value that they give you in the question. In part C, the cylinder was initially pushed down a distance of x is 0.250 metres. That is x naught in your equations because it's your maximum amplitude. Determine the maximum kinetic energy of the cylinder. Remember, in your data booklet, you are not given EK, you're given E total, which is a half m omega squared x squared. Oh my goodness, sorry, it's been a long day of speaking here. Potential energy is given in your data booklet to m omega squared x naught minus x all squared. No, ignore me. That's just x. That's your x naught squared. My goodness. I should just look at my data booklet before I start speaking. So then that one there is your... ignore me. Right, I'm just going to start from scratch. I've gone off on a tangent and that's not helpful. Okay, in your data booklet, I haven't got it with me. It's on my laptop and I'm trying to use my laptop to record the video. In your data booklet, you're given ET and you're given EP. But you know that ET is equal to EP plus EK. So if you take ET minus EP, you get EK. That's what I'm trying to say. I've just written the equations the wrong way around because I've been doing this for quite a few hours now. My brain is a bit mushy. So you take your knowledge that energy is conserved. Energy total minus energy potential is energy kinetic. If you take the two expressions you have for these two in your data booklet, you will get to this one. You don't remember that, you take it from the data booklet. So we know that maximum kinetic energy, you can also actually, more logically, if I had thought this through, go, okay, well, maximum kinetic energy is just total energy, because when you have maximum kinetic energy, you've got zero potential. So therefore, it's when x is zero in this case. So this disappears. So you've got EK as a half m omega squared x naught squared for your total energy. And then it's just a case of subbing the numbers in and you get to 71.4 joules. Sorry, I butchered that explanation a little bit. Really what I was trying to say is, obviously you're not given this equation. So either you need to deduce it from the data booklet versions, or you need to remember that total energy is maximum kinetic energy. Whew. In part II, it asks you then to draw on the axes the graph to show how the kinetic energy of the cylinder varies during one oscillation. So I've drawn it out at the bottom in case that's helpful. Let me see if I can fit everything in. Not quite. So we know that during one time period you get one full oscillation. So it started from being displaced below equilibrium. It's obviously going to move back to the other side of equilibrium, and then it's going to come back down. That's one full cycle. You know that at extremities, kinetic energy is zero, right? Velocity is temporarily zero. So we know that initially kinetic energy has to be zero. We know that at the end it has to be zero, and therefore also at the halfway point it has to be zero. As you're moving through this though, you're going to have maximum kinetic energy halfway between the two. So you've got maximum kinetic energy at t over 4 and 3 over 4t, right? On its way up, on its way back down, okay? So you needed two full cycles, and you very clearly needed these points to be very obviously either labelled or shown. Okay, in question 12, monochromatic coherent light is incident on two parallel slits of negligible width, a distance d apart. A screen is placed a distance d from the slits. Point M is directly opposite, so that's obviously where you're going to get your central maxima. Initially, the lower slit is covered and the intensity of light at M, due to the upper slit alone, so when this one's covered, is 22 watts per metre squared. We uncover the lower slit and it asks you to deduce 3 marks, so you have to explain how you've got there, the intensity at M. So instead of having one source now, you now have two sources meeting at point M. So you have interference, because you don't have one source anymore, you've got two. So you get 1 mark for recognising that constructive interference happens. So the amplitude is going to double, because clearly they are equidistant to point M. It's going to be constructive interference. That's 1 mark. The second mark is for remembering from one of our topic B theory points, intensity is proportional to amplitude squared. So if the amplitude doubles, the intensity is multiplied by a factor of 4, 1 mark. And then one final mark by taking the original value and multiplying it by 4. You're getting 88 watts per metre squared. Then it asks you to deduce and calculate the wavelength of the light given some parameters. So MP, because you're told P is the first maximum, you know then that that is going to be the slit separation. No, it's not the slit separation. I think I need a break from recording. Oh my gosh. That is the fringe separation. Okay, and if you think about your equation, that is letter S. Okay, so they don't say S, they say distance MP, but you need to recognise that that is truly S. Then it's just a case of converting anything in millimetres into metres. You get 1 mark for substituting the correct values and remembering the equation, and the second mark for converting it into nanometers, because it says that specifically. So you should have got to 560 nanometers there. Oh my goodness. Right, let's see if I can get through the rest of this. Right, in C, the width of each slit is increased. Big D, little d, and lambda remain the same. Suggest why after this change, the intensity at P will be less than at M. So, it doesn't say that the intensity is 0, it just says that it's now less. It's essentially asking, if we've got double slit, why do we suddenly see the central maxima is much higher in intensity and then subsequent maxima are lower compared to what the SL students have been taught, which is that a double slit interference pattern is just a series of maxima, minima, maxima, minima. You just have to recognise that they're asking you to realise that the intensity pattern from the double slit has been modulated by single slit diffraction. They kind of give you a clue by writing it underneath, show that due to the single slit diffraction, the intensity at this point is 0. So they are just asking you to recognise that if you have a lower intensity than expected, it's because it's been modulated by the single slit diffraction effect. It then asks you, if you move 28 millimetres from M, why you have intensity 0 there. So that's a minima. Okay, if you have 0 intensity, you have a minima. So because it's single slit diffraction that it refers to, we're going to write our equation, and we know that theta there is the angle to that first minima. So we know that if we have a wavelength of 560 nanometers with a slit width B of 0.03 millimeters, I can work out the angle in radians to the first minima. Then I can literally say, okay, well, if my distance from my source to my screen is 1.5 meters, and my distance from the central point M is 28 millimeters, that angle literally is the same value, and I just use trig to prove that. So I can literally say, okay, with the parameters that I've been given, the angle from the central position to 28 millimeters above is going to be 0.01867 radians, which corresponds to the first minima from the single slit diffraction equation. So it's kind of 1 mark for orange, 1 mark for pink there. In question 13, let me zoom in a little bit. We're almost there. Yellow light from a sodium lamp of wavelength 590 nanometers is incident on a double slit. The resulting interference pattern is observed on a screen. Okay, so we can see that obviously from our double slit pattern, we should be expecting maxima at equal distances apart, right? So if we go from the central position, first maxima, second maxima, we should be expecting a maxima from the double slit pattern at A. We don't see that though, we see a minima. It asks you to explain that. So, 1 mark, the diagram shows the effect of single slit diffraction modulation of a double slit interference pattern. 1. While the double slit pattern would be a maxima at position A, this corresponds to a minima predicted by the single slit diffraction equation, which is why we therefore see 0 intensity at that point. We're then basically given the setup where we're given the double slits, we're given the distance to the screen, we are given the distance to A. Now if you look, A would be the position to the third maxima. Okay, so this distance here is the distance between 3 fringe separations. Okay, so you can work out 1 fringe separation by dividing that value by 3. I have messed up on mine. I have done part I first. and then part II second. So sorry, this is actually part III to find the slit separation. So you can see fringe separation is equal to lambda big D over little d. You are asked for the slit separation little d. Lambda you're given in the question, D you're given in the question, and then S is the value that they told you to A but divided by 3, because you're actually only looking for the distance to the first maxima there. And then when you do that, you get a slit separation of 3 times 10 to the minus 4 meters. Reminder, this is part III that I'm doing in this part of the video, although it's in place of II. For part II, it asked you for the slit width. And so slit width is going to come from your single slit diffraction equation. Theta is lambda over b. This theta now is the distance to the first minima. So you are going to look at the single slit diffraction envelope, and you're going to look, that distance to that first minima corresponds to the distance to A. And so you now have your triangle set up. You're literally just going to use your trig. So you've got that distance to the first minima. You've got 7 meters to the screen. You're going to use trig to find theta. So you're going to use tan theta is opposite over adjacent. It's such small angles though that theta is therefore opposite over adjacent. So I'm just doing this value divided by this value to get theta to be able to substitute in for B. And when I do that, I get 1 times 10 to the minus 4 meters. And remember, that's for part II. Last question on the paper. So the double slit is replaced by a diffraction grating that has 600 lines per millimeter. State and explain the differences between the pattern on the screen due to the grating and the pattern due to the double slit. All you've done is you've introduced more slits, essentially. So 1 mark for each of these points. Blue is the state, purple is the explain. You need both bits to get 1 mark. Number 1, the intensity of the peaks will have increased because literally more light can now pass through. There are more slits. Number 2, the fringes are narrower. You should be able to just look at that by looking at the pattern. And then because the area where constructive interference occurs is now smaller. And then lastly, the fringe separation, again, obviously is much larger than it was in the previous pattern because the separation of the slits is now less. And we can see from our equation that if we have slit separation being smaller, our fringe separation will be larger. And those are your 3 points. But remember, you need the state, so what is different about the pattern, and then the explain, why is it that that's the case, to get the 1 mark there.